Hemostasis requires the interaction of platelets, blood vessels, and coag proteins. This video is going to introduce the contribution that plasma protein systems have to secondary hemostasis. Understanding the mechanisms of blood clot formation through the activation of the coagulation cascade really helps reinforce that platelet plug to stop bleeding. So within this video, this chapter will describe the functional interactions of these procoagulant proteins from the classical perspective of intrinsic, extrinsic, and common pathways. Secondary hemostasis is the process in which a stable fibrin clot is formed to reinforce the initial platelet plug. It involves the activation of the coag cascade. This is a series of enzymatic reactions that convert soluble fibrinogen into insoluble fibrin strands. The process is initiated by exposure to tissue factor at the injury site, which activates the extrinsic pathway, while the intrinsic pathway is activated by contact in negative charged surfaces. Both pathways converge at the activation of factor 10, leading to the production of thrombin. Thrombin cleaves fibrinogen into fibrin, which cross-links and stabilizes the clot and secures the damaged vessel, ensuring long-term hemostasis. The traditional coagulation cascade consists of the intrinsic, extrinsic, and common pathways that work together to form a stable fibrin clot. The intrinsic pathway is activated by contact with negative charged surfaces, like exposed collagen, and it involves factors like 12, 11, 9, 8, and some contact factors prekallikrein and high molecular weight kallikrein. Factor 12 activates factor 11, which activates factor 9, and factor 9, with the help of factor 8, activates factor 10 in the common pathway. The extrinsic pathway is triggered by tissue factor, which is exposed after vessel injury. Tissue factor binds with factor 7, forming a tissue factor 7A complex that directly activates factor 10 in the common pathway. The common pathway is both the intrinsic and extrinsic pathways that converge at the activation of factor 10. Activated factor 10 converts prothrombin, factor 2, into thrombin. Then thrombin converts fibrinogen into fibrin, which forms the mesh that stabilizes the clot. And factor 13 cross-links the fibrin to create that insoluble clot. This system ensures rapid and controlled clot formation following vascular injury. And each of these pathways are evaluated by screening tests such as PTT and PT, which we will discuss in a later slide. Coagulation proteins are a group of plasma proteins that play a key role in the coagulation cascade to form that stable clot. These proteins are primarily produced in the liver and circulate in an inactive form until activated and are called zymogens. That is their inactive precursor protein form. They are represented by a group of Roman numerals 1 through 13, and the assignment is in order of discovery, not really the place in the reaction sequence. Each has one or more common synonyms, and the Roman numeral follows the letter A when it is in the activated form. The traditional cascade is pictured on the left, where you see the intrinsic pathway proteins that include factors 12, 11, 9, and 8. The extrinsic factors that include tissue factor and factor 7. Then coming back together on the common pathway, factors 10, 5, 2, 1, and 13 as a fibrin stabilizing factor. And then we have some regulatory proteins that help prevent these things from occurring in other places besides vessel injury and to prevent excessive clotting. And those proteins are protein C, S, antithrombin, and plasminogen. The next three series of slides are properties of coagulation factors, all divided into the factor Roman numeral, its common name, where it's synthesized, its half-life, its role within the hemostatic mechanism, and if it belongs to a certain group of factors. The first fibrinogen, factor 1, synthesized in the liver, is really the substrate or the precursor to fibrin formation and belongs to the fibrinogen group. 2 is prothrombin, which is also produced in the liver, and it is a serine protease, which is a thrombin precursor, and it belongs to the prothrombin and vitamin K dependent group. Now, factor 3 and 4 are not really considered into the coag cascade as measurable for deficiencies or inhibitors, such as tissue factor is really exposed during subendothelial injury, and it's really a cofactor found in circulation. And calcium is not really protein, it's an element that it's consumed with dietary sources. Proaccelerin is factor 5, it's produced in the liver and belongs to the fibrinogen group. Factor 7 is proconvertin, which is a stable factor produced in the liver. It's also a serine protease, and it's really the constituent of the extrinsic 10-ase complex pathway, belonging to the prothrombin group and is vitamin K dependent. Factor 8 is the antihemophilic factor, commonly known in conditions of hemophilia A. It's synthesized by endothelial cells, and it's complex with von Willebrand factor in circulation in the extrinsic 10-ase complex belonging to the fibrinogen group. Von Willebrand factor is produced by endothelial cells and megakaryocytes and helps with platelet adhesion and stabilization of circulating factor 8. Factor 9 is plasma thromboplastin component produced in the liver. It's a serine protease, and it's a constituent of the intrinsic 10A complex, which has also been associated with hemophilia B syndrome. It's a part of the prothrombin group and is vitamin K dependent. Factor 10 is a Stewart factor produced in the liver. It's a serine protease and is a constituent of the prothrombinase complex belonging to the prothrombin group and is vitamin K dependent. Factor 11 is a plasma thromboplastin antecedent produced in the liver. It is a contact factor belonging to the contact group. Factor 12, high molecular weight kallikrein, and p-kallikrein are all contact group factors produced in the liver, and they're proteases that initiate contact when the vessel is injured. Factor 13 is a fibrin stabilizing factor produced by liver and platelets, and it helps stabilize that insoluble fibrin clot. The prothrombin group includes coag factors that are vitamin K dependent. They are synthesized in the liver and require calcium for their activation. These factors play a critical role in the coag cascade, particularly in the extrinsic, intrinsic, and common pathways. Unlike some other coag factors, these groups of proteins are not consumed during clot formation, except for factor 2, which then converts to thrombin. Now, these factors are vitamin K dependent because they need vitamin K for carboxylation of glutamic acid residues, which allows them to bind to calcium and adhere to phospholipid surfaces. Now, calcium is essential for the activation and function of these platelets, factors, especially in promoting the binding of these factors to those phospholipid membranes. The fibrinogen group refers to a set of coag factors that are consumed during clot formation and play a critical role in stabilizing, forming, and regulating blood clots. They're involved in the formation and cross-linking of fibrin and the protein mesh that forms the final stable clot. Unlike the prothrombin groups, these factors are not vitamin K dependent. And because these factors are completely used up during the clotting process, they are called acute phase reactants, and meaning that their levels will increase during inflammation, infection, or trauma. And really, without this group, thrombin converts fibrinogen into fibrin, forming that structural scaffold of the clot. As a review of primary and secondary hemostasis after vessel injury, primary hemostasis occurs rapidly to form a temporary platelet plug at the injury site, starting with vasoconstriction. There's injury to the blood vessel causing the release of endothelium from those cells, leading to vasoconstriction, which reduces blood flow and limits blood loss. The endothelial cells, the lining is disrupted, exposing collagen and von Willebrand factor in the subendothelial matrix. Platelets then adhere to exposed collagen via those glycoprotein receptors on their surface, which bind to von Willebrand factor. From this adherence, they change shape to form spiky forms, increasing the surface tension for interaction and activation. The activated platelets release ADP, serotonin, thromboxane A2, which recruits and activates more platelets. Platelets then link to one another through these glycoprotein 2B3A receptors, binding to fibrinogen that forms that temporary platelet plug. Now, secondary hemostasis stabilizes that plug by forming an insoluble fibrin clot through the coag cascade. The coag cascade activation is initiated by the extrinsic pathway via tissue factor and the intrinsic factor pathway via contact with negative charged surfaces. The formation of thrombin is next. The extrinsic and intrinsic pathways converge at factor 10, which, with factor 5, forms that prothrombinase complex. This complex converts prothrombin into thrombin. Thrombin then converts fibrinogen into fibrin monomers, which polymerize into fibrin strands. Then factor 13A cross-links those fibrin strands, creating that stable insoluble clot that reinforces that platelet plug. So the combination action of the platelet plug and fibrin network form a durable clot that remains in place until the blood vessel is repaired.